Let's dive right into this explainer and learn how to make the absolute best decisions mathematically when you're faced with strict real-world limitations. Our goal here is completely comprehensive. We want you to fully understand the mechanics of optimization, taking you from the very basic concepts all the way up to building a fully functioning mathematical model yourself.
So, what do a student, a farmer, and a local bakery actually have in common? I know it sounds exactly like the setup to a joke, right? But seriously, think about the everyday reality of these three vastly different scenarios. A student planning out their evening, a farmer planting next season's crops, and a bakery desperately preparing for the morning rush.
Well, the real common thread here is that everyone, from a student cramming for exams to a business owner managing production, needs a truly systematic way to optimize their lives. We all face tough choices. We are all bound by limited resources. And ultimately, we all share that exact same goal of achieving the absolute best possible outcome for our efforts. Here's a quick look at our blueprint for today. We're covering everyday choices and limitations, defining linear programming, the four core components, translating words into mathematics, and finally, building a complete model. Okay, jumping right into section 1, everyday choices and limitations. Let's look at the harsh reality of constraints. Whether you are a student rationing exactly 5 hours of study time between homework and online modules, a food stall trying to maximize income but constantly running out of ingredients, or a print shop managing your ink and labor, you are constantly forced to find that perfect balance. You literally can't just do everything. You have a goal, and you have a strict limit. Moving on to section 2, defining linear programming, exactly what it is, and just as importantly, what it isn't. So rather than just relying on a gut feeling, linear programming gives us a highly systematic mathematical way to organize our decisions. It lets us achieve the absolute best result, whether that's maximizing your profit or minimizing your costs, using straight-line relationships and clearly defined rules. But you have to be careful here, because not every single decision can be solved this way. To be an LP situation, you absolutely must have a measurable goal and clear mathematical restrictions. So planning meals with specific nutritional limits, like tracking your daily protein, perfect LP situation. But choosing what clothes to wear to a party, that's totally subjective. There are no hard mathematical constraints on your style, so it is definitely not an LP situation. Let's hit section 3, the four core components. This is the ultimate blueprint of an LP model. Every single linear programming model in the world is built upon these exact 4 pillars, always constructed in this specific order: identifying decision variables, writing the objective function, writing the constraints, and adding non-negativity restrictions. If you master these 4 steps, you can optimize almost anything. Let's break those down a bit. First, your decision variables are simply the unknown quantities you want to figure out, usually represented as X and Y. Second, your objective is your grand goal, like maximizing revenue. Third, your constraints are your harsh real-world realities, limited time, materials, budget, whatever it is. And fourth, while the variables and goals make sense intuitively, remember that non-negativity is literally always present. Why? Well, because in real life, a bakery can't magically produce -3 cupcakes, right? The math has to stay grounded in physical reality. Section 4, translating words into mathematics. Think of this as your secret decoder ring. The biggest hurdle most people face isn't actually the math itself. It's translating messy, everyday English into structured equations. Keep this translation matrix handy. Knowing that a phrase like no more than translates instantly into a less than or equal to sign is basically the master key to building accurate constraints. If you mess up the translation here, your final model is going to give you completely wrong advice. Let's look at a quick example straight from our source material. If a school canteen is restricted to using at most 30 oil units per day to fry snacks, our translation matrix instantly tells us that our constraint equation has to end in less than or equal to 30. It's just a simple word match, but it perfectly boxes in our mathematical boundaries. Okay, section 5, building a complete model. This is where we finally put it all together. Here is our scenario. We've got a local bakery trying to maximize profits on cupcakes and cookies. They earn 15 pesos per cupcake and 10 pesos per cookie. But here's the catch. They are severely limited by a 300-minute baking window for the day, and they know from their market research that they cannot sell more than 40 cupcakes. Plus, a cupcake takes 5 minutes to bake, while a cookie takes 3 minutes. So how on earth do they optimize this?
Following our 4-step blueprint, step 1 is defining our unknowns. What exactly are we trying to figure out here? Well, we need to know how many of each treat to actually bake. So we let X equal the number of cupcakes to produce, and we let Y equal the number of cookies to produce. Super simple and clear.
Step 2 is writing out our objective function. What's our ultimate goal? We want to maximize profit, so we explicitly state maximize P. And since we make 15 pesos on every cupcake and 10 pesos on every cookie, our equation becomes maximize P equals 15X plus 10Y.
Now for steps 3 and 4, we translate our limitations. That 300-minute limit becomes 5 minutes times X plus 3 minutes times Y must be less than or equal to 300. Our 40 cupcake cap simply translates to X is less than or equal to 40. And finally, we slap on our realism check, the non-negativity rule. X is greater than or equal to 0, and Y is greater than or equal to 0. And this brilliantly illustrates how all those individual little steps finally snap together. We've moved from a messy, real-world paragraph of business realities right into one elegant, fully formulated linear programming model on paper. We've clearly defined our variables, stated our objective to maximize profit, listed our time and demand constraints, and made sure our variables stay positive. It's totally ready to be solved.
So, we've broken down exactly how students, farmers, and bakers can systematically conquer their limitations. Now that you possess this incredibly powerful blueprint for systematic decision-making, what messy real-world problem are you going to optimize next? Think about your own time, your own budget, or even your own business. The math is literally just sitting there waiting to give you the perfect answer.